The last one is distortion will be decreased. Keep in mind the word difference between the word distortion and noise. Distortion is a results from the signal itself. See, signal dependent is distortion, whereas noise is signal independent. We are only discussing the distortion created by nonlinearities in the amplifier for an input signal X, and that nonlinearities, effect of the nonlinearities will be decreased by the feedback connection. What it implies is that this feedback connection makes this circuit now more linear compared to what it was earlier by decreasing the distortion. We need to prove that. Let me do that. In the open loop case, y is equal to A1 times there is some nonlinearity in this amplifier. So, the output y is not just linearly proportional to x, but it also has a components corresponding to higher order terms due to nonlinearity. Now, what I will prove to you is, try to prove to you is that if you apply feedback, the components corresponding to higher order terms in the output compared to the fundamental term or the first term in the feedback case, ratios are much larger, much better. The distortion decreases. So, in the closed loop case, the situation is y is equal to A1 times XE right. As far as the black box is concerned, is input now. So, y will be equal to that, and now XE is nothing but A1 times X minus XF. Which is equal to A1 times okay. So, you can now write down an equation by reorganizing this y in terms of x from here as a function of beta also. Are you with me? But that is a bit troublesome to do. So, let us do it as the following, that let us call this as A1 times x. That means this feedback connection gives you some amount of distortion for the input signal x with appropriate coefficients A1 and A2, which are different from the coefficients A1 and A2 because of the feedback. Let us find out what is A1 and A2 in terms of beta and in terms of the previous A1 and A2. Under no feedback condition, there is a A1 A2 is the coefficient corresponding to the linear term and the second order term, whereas in this case now A1 and A2 are the components due to linear term and the second order term. This A1 obviously will depend upon A1 and A2 and beta. So, let me find out the relation for A1 and A2 in terms of, and similarly A3, so on and so forth. How do we do that? The way to do that is quite simple. If you take dy by dx and make x is equal to 0, what do we get in this expression? A1, right? So, A1 by definition is equal to dy by dx with x is equal to 0. A1 is equal to this, and A2 is equal to d square y by dx square with x is equal to 0, and so on and so forth. So, I can find out the small a's by doing this operation on this y, which contains A1, beta, A2, so on and so forth. Only thing is y occurs on both sides. So, when you take a derivative, you will have to take derivative on both sides also and substitute dy by dx is equal to 0 on both sides. And if you do this, you will get A1 is equal to and so on and so forth. The terms may not be looking exactly like this, but the denominator terms will be, for next one will be cube here and fourth power and so on and so forth. The fact is that A1 of course is A1 divided by this, the fundamental component, not the linear component decrease no doubt, but when you look at this, this is decreased by further factor of 1 plus A2 beta square. So, if you take the ratio of this to this, there is still a reduction by factor equal to 1 plus A2 by beta, and A2 beta is assumed to be reasonably large with the feedback connection that you have here. So, that the second distortion due to the quadrature term will be larger, will be reduced. Okay. So, this is a proof of this, that the distortion content will decrease by providing the feedback. This is another advantage of providing feedback to this. But what are the issues? Why don't everybody do it? Of course, we do it, but before we do it, what precaution do we need to take? Let us get back to our original equation. Came out to be A divided by 1 plus A beta, right? Overall gain of the feedback connection came out to be A divided by 1 plus A beta. In principle, this could be a function of S, as we have seen just now. This would also be a function of S, and this would also be a function of S, right? That means the feedback connection here may not be purely resistive feedback. The network does not contain only resistors, it may also contain inductors and capacitors. As a result, this XF relation to Y, the phasor relation, will have a dependence on frequency. So, I am writing this transfer function as equal to B of S. So, this is a very general result, that when you have a feedback, AS is assumed to be stable, meaning there will be open loop condition. If this amplifier is not stable, it starts oscillating, then the amplifier has no meaning. So, amplifier originally is assumed to be stable. So, AS is having, what does stability mean? Poles of this are in the left half plane. So, AS will have poles in the left half plane. However, when you do this feedback, then you get a new function which is the transfer function. This new transfer function, there is no guarantee that the poles of this new transfer function will remain in the left half plane. That depends upon the A as well as beta. So, we need to study when we do this feedback connection, after the feedback is the network stable or not. If the amplifier goes into oscillation, then there is no purpose.